In this video, we're going to talk about binary search trees. Specifically, we're going to talk about what a binary search tree is and how we use them in code. Later videos will discuss the actual implementation in a little more detail. So a binary search tree is a tree where for any given node, all nodes in the left subtree of that node have values less than the value stored at the node, and every node in the right subtree of a node has values greater than the value stored at the node. So for example, let's take the node that holds 4. Its right subtree consists of this node and this node that hold 1 and 2, both of which are less than 4. The right subtree has 7, 5, 8, and 6. All of those are larger than 4. And that holds for any node in this tree. So here, this node holds 12. Its left subtree has 10 in it. Its right subtree has 13, 15, and 14. This node has 15. Its left subtree has 14. So again, that property continues to hold. Here's another example of a search tree. We're using letters instead of numbers, but that's not a problem. Anything we can compare, we can put in a binary search tree. And you'll notice for the node J, everything in its right subtree is greater than J. It comes after J in the alphabet. Everything in the left subtree comes before J in the alphabet. And again, for simplicity's sake, we'll typically, when we're talking about trees, refer to individual nodes by the element they hold. So we'll say that this is node 12 and this is node 10, but that's just for convenience. Keep in mind that the node itself holds the value 10. So let's see how we work with binary search trees. So you can see that I'm importing the JSJF linked binary search tree class. So I'll create a binary search tree reference. And the search tree is going to hold integers. I'll call it T, and that's going to be a new linked binary search tree that holds integers. And I'll fill that binary search tree. So here I'm filling the tree with random numbers up to 100. And I have an error here. So it was pulling in the wrong module's binary search tree abstract interface. And so now it looks like that cleared up that particular error. So let's add extra nodes, and we're going to make these all 10s. And that's going to, when we run, we'll be able to test our remove all occurrences function. And so I'll add 4 extra 10s. So there may already be some 10s here, but this is just to be sure we have multiple elements. So we've already seen add element. Let's take a look at what else we have in the interface. So we have our binary search tree interface. It extends the binary tree interface because a binary search tree is a binary tree. But the main thing it adds is this add element function. So with a binary tree, if you'll remember, we had to actually create the tree from scratch. With a binary search tree, if we say, hey, I want to add something to that tree, it's clear what it is we actually want to do there. So I also have some remove methods. Remove element removes a single element that matches the target. If there's multiple of the same element in our tree, which is possible, we can call remove all occurrences, which will remove every occurrence of a particular target element, versus remove element, which just removes one. And then we have methods to remove the min and the max value of the binary search tree. Since a binary search tree is sorted, we know where the min and we know where the max value is located. We also have methods to find min and find max, which tell us the largest or smallest element that is stored in the list. So we'll see the implementation later. For now, let's just see some examples of actually using a list. So I can print the tree if I have a toString implemented. And so there you can see my tree. And we can find elements in our linked tree. And we can also do traversals. So let me make that a print. So what I'll do is I will have an integer iterator. We'll do a preorder iterator, and then while preorder has next, I will print preorder next. And let me add a space at the end just so that there's something there. And then once I'm done, I'll print a new line. So let me copy these lines. We'll do an in order, a post order, and a level order. So there's that one. Actually, let me move that because I want to do the in order first. And then finally, we'll do a level order. I think we have everything good there, so let's print what we have. This should print each of these traversals. And you'll notice the in order traversal prints the elements in sorted order. And that's because, if you'll remember, an in order traverses the left subtree, the root, then the right subtree. While the left subtree is all less than the root, the right subtree is all greater than the root's in the middle. And so you can see that if you do an in order traversal of a search tree, it will print the elements in order. So let me put a statement here that we're doing some traversals. And one more thing, let's test remove all occurrences. So we'll print the list before and after, and in between, we'll remove all occurrences of 10 in the tree. So let's run this. And you can see there's 4 10s here and they're all removed. Now, if I run this again, here we have some smaller elements than 10. So you'll notice the 10 is between 5 and 13. And here we have 5 and 13. We're not limited to just integers or characters. We can also have any type of object in our binary search tree. So here's a student record class that's pretty similar to what we've seen before. And the student has a name, a number, and a GPA. We initialize the student number based off of a static integer that we increment each time that we create a student. And then everything else is pretty standard. We have getters and setters, toString. We've overridden equals and compare to, though, because we have to put comparable objects in our binary search tree. If the elements we put in there are not comparable, then there's no way to tell where they go. So let's declare a binary search tree of student records that we'll call S. And I will add some students. And now let's print our tree. So now you see that it prints these student records. So I'm going to create a list of some names that I can use for testing. Now, what I'm going to do is I'm going to have some test code that's going to try to find these students in my tree. And if we go back here and look, we notice that we see there is a Mark Hamill, but there is no William Shatner. So I want to print the results of find here. But the question is, how do I find the student record? Because I don't know their full student record. I know just their name. But keep in mind that the compare to for student record actually compares the names only. So I only need a record that has the name. That's sufficient to do a comparison. So what I can do is I can find a new student record with that name, and the GPA doesn't matter at all. So now, if the find fails, then I'm going to print a message. So let's take a look at what happens here. And so now you can see it is able to find Mark Hamill. It's not able to find William Shatner. So hopefully that gives you an idea of how you can work with binary search trees. In our next video, we will go over the implementation of a linked binary search tree.